All right, in this video we will do the 2018 AMC 10A problem number 16. Right triangle ABC has leg lengths AB equals 20 and BC equals 21. You should immediately infer that it's 20, 21, 29. You should know your Pythagorean triples. There's quite a few you should know. All right, including AB and BC. Real quick, B is the 90-degree angle because it's part of both legs. So we'll put B here, A here, and C here. And we'll connect like this. So then this will be 20 and this will be 21. It says, including AB and BC, how many line segments with integer length can be drawn from vertex B to a point on the hypotenuse AC. Okay, so if we think about this, we're looking for some kind of a restriction, a parameter that we can operate within. And that's going to be the shortest distance from a point to a line is perpendicular. So if we draw that height in to find out what it is, it's basically the height of the triangle going the other direction. So what we can do is we can say that base times height equals any other base times any other height. This will be 420, this is 29, and we'll do 29 goes into 420. I think it's 14 something. 29 goes in once, you get 29, you're going to subtract to get 13. 29 goes into here 4 times, you're going to get 16. Yeah. So you get 14 left. It doesn't really matter what you get because it's going to be a decimal point after that. So what we have is 14 point something, okay? So that's what this length is. The shortest distance from B to AC is more than 14. That means you can never have a length of 14 from B to AC. Continuing on, you must be able to hit every other length until you get to 21. That means you can hit all of the values from 15 to 21 inclusive. 21 minus 15 plus 1 is 7 for that side. Now, what you want to check really quick is does it say how many integer values can the lengths be? No, it doesn't say that. So we know that we have to check the other side too. You can have two side lengths that both have the same length as long as they're not the same segment. So over here, you're going to go from 15 to 20 inclusive, which is going to give you 6. 7 plus 6 is 13. Continuing on with the 2018 10A problem 17, which was also the 12A problem 12. Let S be a set of 6 integers taken from the set of integers from 1 to 12 inclusive, with the property that if A and B are both an element of S and A is less than B, then B is not a multiple of A. What is the least possible value of an element in S? Okay, so how do you progress in this problem? You just try the answers out. So let's just see if we can prove that 2 can be used or not used. If 2 was going to be used as the smallest element of S, obviously 1 can't be used, then no other even number is allowed. So we could list all the odds, 3, 5, 7, 9, and 11. However, 9 is not allowed if 3 is there. So they can't both be there. You can have one or the other. That only gives 5 elements, and that's not going to work. So the answer is not A. We try 3, same thing. If the smallest value is 3, you cannot have 6, 9, and 12. You can have 4, 5, no 6, 7, no 8 if you have 4. So we could have 8 or 4, but not both. Just keep the 4. 9's not allowed. 10 can't be there because of 5. 11, 12 cannot be there. Again, this is only 5 elements and does not work. Proceed to the next one, 4. If we try 4, then no 8 and no 12 is allowed. We can have 5 and 6 because they're not multiples of 4. Neither is 7, no 8. 9's okay because 3's not there. 10's not okay because of the 5, but we don't need it because we have 11. 1, 2, 3, 4, 5, 6, that works, therefore The answer is C. In this video, we are going to look at the 2018 AMC 10A, problem number 18. In this video, it talks about how many non-negative integers, as you're reading, try to process. Non-negative doesn't mean positive, it can include 0. Can be written in the form a sub 7 subscript, so you say a sub 7 times 3 to the 7th plus a sub 6 times 3 to the 6th, all the way down where the subscript matches the exponent on 3, where a sub I is an element of the set negative 1, 0, or 1, for I between 0 and 7 inclusive. This problem's difficulty somewhat is the notation. For a lot of people, they don't know what the symbol means, or they don't know how to handle a sub I. What does it mean that I is between 0 and 7? We can kind of analyze it. This I is matching the subscripts on each of these numbers, 7, 6, 5, 4, down to 0. So if those numbers range from 0 to 7, that's why it says I ranges from 0 to 7. So for any given one of these coefficients of the power of 3, say a sub 2, it can only have the values negative 1, 0, and 1, and all of them have that property. So where do we begin? It can feel like, again, a problem we've never seen something quite like before. Just start wherever you can. Just play the what if game. What if a sub 7, it's going to be the most powerful one on here because it's at 3 to the 7th. What if a sub 7 equals negative 1? What if that happens? 3 to the 7th ends up equaling 2187. 3 to the 6th is equivalent to 9 to the 3rd. You should probably know your perfect cubes through about 12. 3 to the 6th is 9 to the 3rd, which is 729. 3 to the 5th is 243. 3 to the 4th is 81. Cubed is 27. Squared, 9. First, 3, obviously. And the 0 power, always 1. So if this value was negative, I would have negative 3 to the 7th. I would have a negative 2187 in my problem. If all of the rest of the numbers, if all of them came out to be positive 1, and I added all of them up, would it be enough to overtake the negative 2187 and generate a non-negative integer? It would not. You can see right here this is about 1,000, and you're not going to get another 1,000 from these numbers down here. So this number is very powerful as the top number. If it's negative 1, no such numbers exist. Before we explore what happens if it's 0, let's change it to positive 1 then, because obviously if it's positive 2187 you're starting off with, all of the rest of the values can take on whichever value they want, and all such numbers will be a non-negative integer. Then that means we have how many choices for the coefficient of 3 to the 6th? We have 3 choices. So those 3 choices then times the 3 choices we have for 3 to the 5th, and so on. Each of these has 3 choices for negative 1, 0, and 1. How many of these are there? From 6 to 0, there are 7 numbers. So you're going to have 3 to the 7th choices, and we've already calculated that. If a sub 7 is 1, you get 2187 such numbers. In fact, from doing this one what if, we can now perceive what's probably going to happen the rest of the way. Let's see if we make a sub 7 the only other option, 0. If we get a sub 7 equal to 0, then a sub 6 now becomes the most powerful player on the board, and we want to make it positive, which can only be achieved with positive 1. So if a sub 6 is 1, now all the rest of these can take on any of the 3 values, and you can see the problem just cascades from here. In each scenario, we're going to get this amount, and all the way down that many integers. If we add all of this up, though, we only get 3280. So where do we get from the answers? You can tell it must be D. It's clearly not E. So how do we get the extra 1, though? Well, again, it said non-negative. What we're doing in this process is we're making the leading coefficient, they're all zeros except for the one that starts off the next set. And so if they're all zeros except for this one, we're saying that a sub 0 is equal to 1, and that's why we get this one scenario. There's one more case where all 7 numbers, all 8 numbers are zeros. All the coefficients are. That gives you 3281. And continuing on with the 2018 10A problem 19. A number m is randomly selected from the set 11 to 19 odd numbers, and a number n is randomly selected from the set 1999 to 2018, all the integers inclusive. What is the probability that m to the n has a units digit of 1? The first thing you have to do is remind yourself not to panic. Just start thinking about things. It's a probability problem. Probability is number of favorable outcomes over number of possible outcomes. So what we want to do typically is find the denominator of that expression first, the number of possible outcomes. It's usually easier to find, and once you've found it, you'll feel a lot more comfortable moving forward. So our denominator possible outcomes is there's 5 possible outcomes for m, and if I take this, subtract this, and add 1, I'll get that there's 20 possible outcomes for n, and 5 times 20 is 100. You multiply them because they're independent events. Okay, so we have 100 possible outcomes. Now how many satisfy the condition? This is just counting now. So we're just going to say, again, if you're not sure how to progress, just play what if. What if m was 11? Okay, the thing about units digits is they don't care about the other digits. So 11 to any power will have the same units digit as 1 to any power. And the fact is 1 to any power is 1, so 11 to any power will always have a units digit of 1 as well. So you're going to get, if m is 11, all 20 values of n will work, and we can simply put 20 plus. Next up, what if m is 13? Again, we disregard the tens digit and just think about the 3. Now you can do this with modular arithmetic and modding and stuff like that. I just want to do it with the powers themselves and make it a little easier to think about in that way. So 3 to the first is 3. 3 to the second is 9. 3 to the third is 27, but again, we're only writing the units digit. 3 to the fourth is 81, which is 1. 3 to the fifth is 243, which is 3. And from here you can see it's going to repeat. Again, the units digits don't care about the other digits. So we have a cycle of 4 things, the fourth of which is our desired 1 in the units digit. So how many multiples of 4 are there in these values, since these are the exponents? You're going to have 2000, 2004, 2008, 2012, and 2016. All 5 of those will give a units digit of 1 for 13. So we add 5. Next you go to 15, and there's none. 5 to any power is never going to end in 1. It's always going to end in 5. You do the 7s next. 7 to the first is 7. 7 squared is 49. 7 to the third is 343. And 7 to the fourth is 2401, I want to say. So 7931, when you do 7 to the fifth, you're going to get 7. Again, the cycle is 4 things, just as it was for 3. And again, the fourth one of those things is the one that we care about. So it's going to have the exact same powers that turn 17 into a units digit of 1. Again, there's 5 of those. Now we do the 9s. To explore 9s, 9 to the first is 9, 9 to the second is 81, 9 to the third is 729, and you can see it's going 9, 1, 9, 1. If you do one more, 9 to the fourth is 65, 61. Is that right? No. Yeah, actually that's right. Okay, so then what? We see that the even powers are 1s in the units digit. So if I think about that, how many even numbers are there for n? Because again, n is the exponent. Obviously, you're going to have 10 odds and 10 evens. So there's 10 more. 10 plus 20 is 30, plus 10 more is 40 over 100, which simplifies to 2/5. Hello, in this problem we will do the 2018 AMC 10A, problem number 20. A scanning code consists of a 7x7 grid of squares with some of its squares colored black and the rest white. There must be at least one square of each color in this grid of 49 squares. A scanning code is called symmetric if its look does not change when the entire square is rotated by a multiple of 90 degrees counterclockwise around its center. Keep in mind, because it's a multiple of 90, we could just go clockwise if that's easier to think about for you, because it's going to accomplish the same thing. Nor when it is reflected across a line joining opposite corners or a line joining midpoints of opposite sides. What is the total number of symmetric scanning codes? Okay, in the problem, there was no grid given. So I drawn this grid to save some time for the problem, for the video. A lot of people just think, how am I going to do this? Number one, this is a primary reason you need to bring graph paper. Because if you have graph paper, you've already got a 7x7 grid. Just outline it and you're ready to go. In the absence of bringing graph paper, which is allowed on the test, you'll have to freehand draw it, which is what I've done. Okay, so rather than get all bogged down with everything, just start going through and thinking about it. The center square is not really that important. We're going to give it like an X to mark it as the center square. It can be either black or white because when you rotate, it stays the center square, and when you reflect up or down, it'll stay the center square. From there, build out. Think about what squares will reflect onto other squares. So if I have this square, which I'm going to give it an O, if I was to rotate 90 degrees clockwise, it would end up here, 180 here, and 270 here, or 90 counterclockwise, same thing. Incidentally, if I fold this over the middle line with a reflection, these two will end up over here and vice versa, and folding down this way will fold the top to the bottom. So all of these will have to be the same color, either all black or all white. Okay, next up, we've got this one. We'll put minus signs in the box. Okay, so these ones will all reflect onto each other as well by both rotations and reflections. Okay, build out to the next square out. We'll put a diagonal slash here, a diagonal slash here, one here, and one here. This works just like the 4 circle corners. Next up, let's do, I don't know, a spiral right here. And this time, if you think about the diagonal from corner to corner, this will also be a spiral. If I reflect over the midline here, this will be a spiral, and this will be a spiral. Similarly, reflecting up will give me a spiral here, and a spiral here, and here, and here. Okay, so you don't have to use these symbols. You could use numbers or letters, you know, it's up to you. I'm just choosing to use symbols. Next up, this square here, I don't know, let's give it a triangle. We'll have a triangle here. This will have to be a triangle by a 90-degree rotation, this by a reflection or 180 rotation, and same with this one. Okay, let's work our way out to these 4 corners here. We can put like a smile in each of these, or a U, something like that. Next up, we'll do these ones. We'll put a plus sign, and it looks just like the spirals in the previous level. This will go here, and here, and here, and here, and here, and here, and here. Next, we'll have this one, this one, this one, this one. Working around, what can we give for that symbol? It doesn't really matter at this point. Let's do a C or something going sideways. So we'll go like this, and it will also go here, and here, and here, and here, and here by reflections, and also here. And lastly, we'll leave the white square blank. And this represents every one of the same shape symbols or blocks or squares has to have the same color, all black or all white. So let's count up the symbols. You've got 1, 2, 3. That takes you to the second round. 4, 5, 6. That's going to cover your next layer square. 7, 8, 9, 10. 10 being the blank square. So each of those squares, when you think about it, has two choices, black or white. So it's 2 times 2 times 2. How many times 10? So it's going to equal 2 to the 10th. That appears to be how many solutions we have. An easy way to remember 2 to the 10th is that the 10 just transfers to the number, and it's 1024, half of the famous game 2048. So 1024 is not in our answers, and for many of you, it's probably a good thing it wasn't, because it would have been a really good trap answer. However, why is it not? It must be B or A, but most likely B. Why? Think about why it would be. It's because it says there must be at least one square of each color. So from these 1024, we have to subtract the two cases that were all white or all black, giving us answer choice B.